We're going to get started. So I'll give you a little preface, if you will. I'm pretty certainly one of the youngest presenters here, except, of course, for Theo. They grow up so fast, and we're all so proud of him. But I'm trying to do this thing that no one in my, well, not no one, but a lot of people in my generation seem to forego, and I'm going back and looking at things that other people have done before, maybe even outside of my discipline. And I'm an engineer, but I'm a weird engineer. I have a BA in things that have nothing to do with engineering, and it sort of all happened by accident. So I think about random things that have nothing to do with engineering while I'm engineering. So this talk, by the way, so that no one's disappointed halfway through, won't be about our crazy storage system or like indexes or any of that. It won't be about our product or what we do. It's strictly about laying out an architecture in a way that keeps you sane. And in a way that sort of encompasses the principles that become even more important when you're in the cloud. And so we'll get to that without further ado, right? So SimpleGeo, the reason all this is important to us is that we are, I believe, a platform as a service. I honestly have lost track of all the different abbreviations, but what this means is that if we have an outage, a bunch of apps have an outage. The same way when Amazon goes down, half the internet goes down, except we're obviously a lot smaller, so not half the internet will go down. But regardless, it's bad news when we go down. So we spend a lot of time thinking about this. And the company, as a company, we take this very seriously. We do the same thing Heroku does, where I'm on call every fourth week, and everybody else in the company is on call every fourth week. And stuff becomes important to you when at 4 a.m. you get texted, and it's this thing that's totally not actionable. But your girlfriend still woke up. She's still pissed because you got texted, and you don't have to do anything. But you start to care about these things really quickly. So we're going to talk about our sort of organizational goals, and you'll see that they're also your organizational goals. And then we're going to go through a little bit of theory, and that's what I'm talking about when I say we're going to talk about things other people have done. Then we're going to examine how that theory applies even more in the cloud, and then we're going to go over actual architecture and implementation details for SimpleGeo. So our goals probably won't surprise anyone, right? We want to be highly available. We want to be linearly scalable. We want to be elastic and flexible, and we want to be fault tolerant, right? Don't wake me up when something goes down is the short version of that, right? I don't want to have to actually get out of bed when I get paged. I want to look at it, maybe pull out my laptop, do a couple of things, go back to sleep, deal with it in the morning. More importantly, our users don't get woken up, right? Because in our case, if we go down, it's not like someone can't get to their photos. It's someone not making money because their app's not up. So they get stressed out real easy too. So basically, anyone that runs services, right? This is familiar to all of you. That's a common problem. So we're going to go through a little bit of theory that actually the main book that I'm basing a lot of this stuff on was written before I was born. It was published in 1983, and we're going to look at the internet as a series of complex systems, and internet architecture as complex system. So the book is Normal Accidents. Has nothing to do with the internet. I don't think Charles Perrow knew what the internet was when he wrote the book. But at the same time, it has everything to do with the internet, and you'll see why in a second. The book is about basically complex systems and the inevitable accidents that happen within those complex systems just due to their nature. The way they induce human error, the way humans basically can't deal with the complexity involved. There's a ton of stuff there that I won't go too deeply into. There's a couple main concepts we'll cover, though. So a complex interaction, the most important thing about that is that it's something that happens that's unexpected and the consequences of which aren't immediately visible. In fact, Ben Fried, I didn't catch the pronunciation, the keynote set me up perfectly because what he described was actually a system failure within his organization. No individual action that he described caused the ultimate state of disarray. And actually, there's a really nice term that I love that describes what happened, which is called drift into failure, where one guy is doing something, and completely unrelated, he blocks this, and it's an SNMP port. No big deal. Everything's fine. There's no problems. Months later, you start accumulating problems. You don't notice them because the SNMP port is turned off, and some other setting gets changed, and someone else didn't know about this, and they did this over here. And these are completely unrelated changes that on their own don't cause any specific jump in traffic or jump in any graph, but combined causes huge failure. And it's also related to the whole thing about if you keep the turning of the temperature while the frog's in the water, the frog will boil. But if you turn it on right away, the frog will jump out. So drift into failure is the gradual boiling. No one wants that. So this is a bit of a long read, but it's important, and we'll get back to this paragraph. So baffling interactions basically result from having complex systems. I'll just read this out loud so you don't get hypnotized by the slide. So the notion of baffling interactions is increasingly familiar to us all. As systems grow in size and in the number of diverse functions they serve and are built to function in ever more hostile environments, increasing their ties to other systems, they experience more and more incomprehensible or unexpected interactions. They become more vulnerable to unavoidable system accidents. So as you add, you want to now have a mail server, and we need to put a firewall around it, and we're going to have a worker queue for this. As your diagram stops fitting on one page, and you start, writing it on a board and taking pictures of it, your mind can no longer foresee everything that's going to happen inevitably, and you end up with baffling interactions. So fortunately, we're not talking about nuclear plants here today. So everybody relax. Nobody's going to die. It's just the internet. However, these are our jobs, so we want to do well. And so this is, can everybody see? Can you see that? That's Walter Sobchak from The Big Lebowski. And he drops this gem, and I was recently rewatching it, and I was like, this is perfect. The beauty of this is its simplicity. Once a plan gets too complex, everything can go wrong. And, this is a kind of a dumb character in a movie. He's not really saying much when he says this, but really, we can all learn a little bit from Walter, because once a plan gets too complex, everything really can go wrong. And this is exactly what Ben was talking about, right? When you have this isolated series of things and no sort of global view of what's happening, you can't deal with it. So the two main concepts we're going to focus on are going to be linear versus complex interactions. And linear versus complex, basically, a linear interaction is like an assembly line, where you put things at one end, and then there's a series of basically mini assembly lines, right, where you go through steps, and one thing comes in, another thing comes out. You know exactly what happens at every step. Nothing's coming in from the side. It's just one straight line. You can stand over the guardrail and kind of look and see exactly what's happening. A complex interaction is the best example is a nuclear plant, right, where you have pipes going all over the place. No one really knows where each pipe goes. And the second concept we're going to focus on is coupling, and this should be familiar to everyone, right? Tight coupling means that there's very little slack. There's only one particular way something can happen, and if it doesn't happen that way, you don't really have recourse. Loose coupling means you can kind of go about it a few different ways. My favorite example of loose coupling is dinner, right? So in order for dinner to be cooked, someone has to go get the groceries. I have to come home and do the dishes and make sure I do them in time and don't put it off for a week. And if I put it off but there's good news, right? Like, if my girlfriend didn't get groceries during lunch, I can go get them after work. Like, it's okay. She can just tell me. If I didn't wash the dishes, she can yell at me, and then I'll wash them later, and just in time for dinner. It's okay. And if we're both lazy and nobody wants to do anything, we call North Beach Pizza, and we still have dinner. It's okay. It's fine, right? There's different ways in and out of the situation, right? We're not stuck to a specific way of doing anything. So you want to be loosely coupled and linear. And I should probably slow down a little bit. I'm a little nervous that we're going to run out of time, but I feel like I'm barreling through this. So the ultimate loosely coupled linear system is the seesaw. And John also talks about this. You're not working on a simple system unless you work on a seesaw. So your most straightforward, stateless, is Twitter down right now.com website is a complex system. I'm sorry. And the seesaw is a really nice example of what I'm talking about, right? Because there's only one thing you can do. And even if your friend is a future All-American lineman and is way heavier than you, it's okay. You can just get him to move a little closer. It's loosely coupled, right? There's slack. There's adjustments to be made. Unfortunately, we're very far from that land. So these are my two favorite slides in the whole thing. So this is from the description of 3 Mile Island. And this is a part of the description of the accident, the nuclear accident back in the 70s. So they found that radioactive water was not traveling to the tank they intended, but because of complex flow and pressure interactions, was going to a different, wrong tank, which also overflowed, this time in the auxiliary building. Bad news, right? Amazon Web Services. The traffic shift was executed incorrectly, and rather than routing the traffic to the other router on the primary network, the traffic was routed onto the lower capacity redundant EBS network. So, I'm glad other people are laughing because I was worried that everybody would be like, well, those aren't the same at all. But they are because they're previously independent systems that no one ever foresaw interacting in any way, shape, or form. No one ever foresaw this happening. Like, well, why would the water go into the auxiliary tank? And because of unanticipated interactions, there was a fundamental surprise. And fundamental surprise is a loaded term that I'm not going to go into because it's beyond the scope of this, but it's basically something that changes your view of the world. Where you realize, oh, it can go into that tank. So yeah, when you pump water into the wrong tank, the behavior of the program is undefined, right? Who knows what's going to happen? AWS goes down. But this talk is all about the cloud, right? I even added like the also cloud. I hope no one feels misled. It's actually not that much about the cloud. The cloud just exacerbates all of these things, and I'll explain why now. So, who's familiar with the trifle analogy for layered web services? Right? So I don't actually know where it originated. I saw it in Cal Henderson's book. So I'll credit him, and he can resolve it later. And this is actually the wrong kind of trifle. If Cal sees this, he'll be mad, because you're supposed to use a British trifle, which only has one layer of each kind. And this is clearly a Canadian trifle, where there's more than one of the same layer. But we'll just pretend that all the layers are different, because this is the best picture I could find. So what's the trifle analogy? So the trifle analogy basically treats the different parts of your architecture as layers, right? So at the top, you have your web servers. That's where everything comes in. And then you probably hit the gooey, fatty layer of cache. Eventually, you hit the data store, and everything resides on hardware that's hosted by your MSP. There's as you get into more trouble, there's layers you can go deeper and deeper, deeper and deeper. If you went to Arthur stock, right, you can, if your data store is behaving slowly and you can't figure out within the parameters of the data store, you dig deeper, you eventually get to the kernel, eventually you call your provider and you say, well, clearly this is something that's your fault. So an important thing to note is that a trifle is a complex system consisting of complex subsystems. So like, right, your memcache server is a complex system, as simple as it is. So it turtles all the way down, unfortunately. So now you're on the cloud, and now instead of hardware and a service provider to call, you have this amorphous blob. And some blobs are more amorphous than others, and someone's going to say, but our blob is less amorphous, and I don't care. You don't have control over the very bottom of your stack, right? You get to a certain level and you have zero insight, especially if your provider modified the software that runs the hypervisor, right? So you don't even know what they're running. Even if you wanted to dig deep, you're not really sure because their changes aren't public. So now you're tightly coupled to another complex system over which you have no control and into which you have pretty much no insight. And the only way this photo could be better is if the puppy was chained to the skateboard. I thought about adding that, but it got a little too morbid a little too quickly, and I backed out. So now we just have the puppy, but you get the point. So recall baffling interactions from earlier, right? There's a reason I brought that up. So now we have the same code, and I highlighted it a little more. So as these systems are built to function in ever more hostile environments, increasing their ties to other systems, they experience more and more incomprehensible or unexpected interactions. So now you have this other system that you don't know anything or almost anything about, and crazy things happen on it. Someone else gets put on the same multi-tenant box, and they're doing tons of I/O. And it turns out that even if they're using a different disk, the I/O goes over some common network that you, once again, don't know anything about. And now your I/O is suffering because this Yahoo over here is, streaming porn from his AWS instance, right? And now your perfectly pristine database is suffering. One example I'll give of this is we actually dealt with this head on, and sadly, nothing I talk about in this talk would have helped us. We discovered that there was some sort of, the details escape me at this point, and it's too depressing for me to go digging and tell you about it in great detail. It's all on the internet. But basically, because of clock drift within the hypervisor, the kernel started saying, oh, this GC thread in this here JVM application has been using 9,999 hours of CPU. I'm not going to give it anymore. And then you're sitting there and you're like, well, garbage collection took 20 minutes. I started writing Java 2 months ago. It seems unreasonable, but maybe I'm doing something really crazy. Maybe I have some crazy object graph. You spend a non-trivial amount of time figuring out what could possibly be taking 20 minutes. I mean, come on, we're clearing some memory, people. And then you run the libc tests, and those fail. And then you start thinking maybe it's not the JVM, right? You start thinking maybe it's below, and you end up figuring out that there's some bug somewhere, either in the kernel or the hypervisor. No one's agreed yet. No one's identified the patch set that fixes this particular problem yet. Everyone's saying, I think it's this one. Run this kernel. So we run it, and everything's fine now. But figuring that out took forever because it was a baffling interaction. There was no sort of reasonable explanation within our realm of understanding for what was happening. So the only thing you can really do, and like I said, none of this would have helped that because that was just 20 minutes at a time, multiple nodes would just hang out and do nothing. They'd stop the world, and then the garbage collection would not come back for another 20 minutes, and then, right. But for smaller failures, which do still occur, you're in the cloud, so you've got the so-called chaos monkey, and not the Netflix chaos monkey, any virtual provider chaos monkey where things just disappear. You've got potential, multi-tenant issues that come and go, and you have no idea when it's going to happen, or everyone runs their crons at the same time, and you have to. If you decouple, you can distance yourself from all that mess. And our sort of mascot for decoupling is going to be the tuned mass damper from a building in Taipei. Basically, what this thing is, it's there to absorb seismic movement in a gigantic building. So what it's really doing is decoupling the building from planet Earth, right? So the building can move maybe a little more gracefully than the Earth that's shaking underneath it. So that's a perfect example of decoupling in the very real world, right? People's lives depend on this giant ball with ropes coming out of it, the workings of which are completely opaque to me. So we're going to go through a few things you can decouple. So we're going to start real basic. You can decouple your subsystems, right? You have different sort of applications you're running. You have your web server, maybe you have your cache server. There is sort of, I don't know what the sort of state of the art is on this. For a while, people would say, oh, well, your web server's not using any RAM. Put your cache on that same server. Maybe don't, because you're opening yourself up to that exact same kind of interaction that I'm talking about, where you're just introducing another possibility for things to rub that you don't really want rubbing. And in a bigger picture, use queues and caches as buffers, right? That's nothing new. The thing that I don't think people think about when they do this, and I definitely think when we added our queues, and we'll get down to that in a little bit, we didn't really think we use RabbitMQ. And a couple people in the company knew RabbitMQ real well from somewhere else, and then I came on, and I had never used RabbitMQ, and I was just like, what is happening? What? I just want to send a message. And then, after a while you learn it, and it's not so bad. But when you introduce these new systems, you're introducing additional complexity, additional ways in which things can fail. By the way, that reminds me, everybody went to lightning talks. Everybody remember the guy that, is he here? It sounded like a cry for help for the first 10 slides. I thought he was going to pull a gun out. He was really, really upset about ops work. The reason ops work is so stressful is that things like that happen that you have no idea where it came from. You have no quick recourse because you don't know what's happening, and everyone's standing over your desk. What's going on, dude? Breathing in your ear, right? Like that. Of course he's mad. So decoupling is one major thing you can do to get rid of the stress in your operator's life. And in your own life, Ben talked about how the sort of fixing the problems that they had took months and was super stressful. You're trying to avoid this sort of thing. So then you can do some sort of, these aren't necessarily recommendations. These are things you can do. We actually don't do these things. I wish we did. And actually, I suggested the first thing at Flickr, and John Allspaw laughed at me. And then later, another guy on the team was like, actually, maybe we should do that. And then we kind of went back and forth. But the point is, you have your node has a primary purpose. Let's say it's a web server. It's got 8 cores, but it's got all this other crap it can do, or it needs to do. You got your SSH connection, right? You got probably running Puppet now, or something along, or Chef, excuse me. In my humble opinion, if you've got 8 cores, there's nothing wrong with saying the web server gets 7, everybody else gets 1, right? Because your auxiliary task, you still need them. And the reason I suggested this was in response to an outage we had where someone deployed some code that it was tested, everything worked. They forgot to test one thing, which was an empty input. And an empty input sent it into an infinite recursion of doing a really expensive calculation. So immediately, every single one of our web servers just went to its knees, to the point where we could not deploy the code to fix it. And so we were sitting there, and the deploy would get like most of the way there, and things could be better about the deploy system, but that's not what we're here to talk about. But the point is, we couldn't fix it because the servers were so hosed we couldn't do anything to them. This would have solved that problem, right? If you could always establish an SSH connection and always copy something to the server, you could work your way out of there. Of course, there's more scientific, robust solutions called containers, and I have Librato up there. There's other options. Librato is the one I know, and we've actually been considering using them. Haven't deployed it yet, but Librato just lets you say, OK, processes in this group get this much CPU, processes in this group get this much CPU, this much memory, and that's it. And so your web server can never run away with the box. Your memcache, if you wanted to put cache on it, you couldn't use more memory than you wanted it to. It's exactly what the CPU affinity solution does, except it's a product that actually is meant for that. So the next thing to decouple is your actual functionality. So most of you probably do work on more complex things than a seesaw, so you're probably doing more than one thing. For example, we have 3 products that are, some of which are related, but in general, they don't really do the same thing. So it makes sense to just separate them. And this is nothing new, right? The service architecture is something that's been talked about for years. No one's learning anything new. It just becomes even more important if you think back to our goals of being elastic and flexible. Let's say you have 3 products. 2 of them are kind of duds. The third one takes off. If your services are separated, you can just spin up 20 more of that, and you don't have to deploy the other services to it and waste resources, right? And it kind of keeps it separate, keeps it neat. From a business perspective, that allows you to say, OK, well, look, I'm getting this many requests for this service, this many users are paying for it, and this is how many nodes I have for that service. Instead of, well, I have 40 nodes. Some of those are probably being used for this product, right? So it just makes everything neat and compartmentalized, which is nice on not just the apps perspective, but sort of your whole business. And it also reduces the potential for those pesky, baffling interactions where you didn't think that having both these products in the same daemon would be a problem, but sometimes this product needs to page in like 2 gigabytes for some reason, I don't know why. And now you're hosing all your other products because they're in the same process on the same box, right? So just contains your stress. This is sort of a kind of one of these things and not like the other, but this actually probably would have, if we thought to do this sooner, we probably would have figured out the kernel problem faster. And this is actually what ended up happening is I spun up my own, we figured out a little program that would trigger the kernel bug that I was talking about earlier. And I said, well, like what? I don't know what's going on anymore. I just spun up my own personal VM, didn't look at, I just picked whatever the default was. It happened to spin up a different version of the same Linux distro that we run, and I ran the program and didn't fail. And that's how we started to figure out that it wasn't anything we were doing. It was right. It was a deeper problem. So the other reason you want this, and there was a lot of talk going on with the big AWS outage. There was a lot of people saying, "Oh, well, you should go multi-platform." Good luck. I mean, that's fine, and that might work. But the thing that my primary degree was in philosophy. Let's think through this in deontological terms. What if everyone did that? Now, this is my favorite thing in the world. It's a human-caused, sort of unanticipated interaction, right? There's no real logical connection between, say, AWS and Rackspace and Joint. But if AWS goes down and everyone says, oh, flip the switch, let's deploy everything to Joint and Rackspace, guess who's going to go down? Joint and Rackspace. And now we're all boned, right? Like, it's not really a sort of sane way for everyone to go about their business. However, now you're starting to see things like Direct Connect, and I don't know much about the other providers, so I'm telling you what I know, right? So Amazon's starting to offer a way to build out your own hardware in a data center very near theirs and directly link to your AWS infrastructure. So if you have some particularly stringent demands, such as I/O for your database, you can just put it on there. So you want your infrastructure to be as sort of your build-out, your deployment process to be as generic and abstracted as possible, so you can just say, you know what, today we're going to switch from Ubuntu to Red Hat. It's going to be a pain in the ass. I'm going to move a bunch of files around, but really I'm just editing Puppet or Chef files, right? And then I just run it, and I don't you just sit there and watch. Same thing as if you're not deploying on a cloud service anymore, you want to be able to it saves you a lot of work later. This is sort of the meat of our approach, right? And this becomes really important in the cloud. Separate your data centers, right? We'll get to some diagrams that will illustrate this really well. But this, once again, isn't just for the cloud. So one of the things that I used to work at Yahoo, and one of the things that I was really, really proud of Yahoo doing is they started building data centers in cold places and just having big windows. And you just did not have an HVAC system in the data center. And when you do that, and when your software layer is abstracted at the data center layer, sort of, where you can say, hey, turn off this data center, let's go to this one. When it gets hot for like 2 days, and I'm basically paraphrasing something, I forget the guy's name, but I recently saw a Yahoo, an ops guy that's been, an exec that's been there for a while, talk about this. If it gets too hot for a couple days in Washington, just turn that data center off while it's hot. And you're done. You don't need to scramble your crew of guys with their backpacks. Oh no, fix the HVAC. There's no HVAC. There's nothing to break. And this is what I was talking about earlier. The more systems you have, the more things will break. So if you don't have an HVAC system, the HVAC system won't break. You just have Windows. It's awesome. And I'm sure they're not the only ones that are doing this. So when you are, especially if you are an EC2, and once again, I won't try to speak to other providers lest I embarrass myself, your availability zone, which is the equivalent of a data center, is your basic sort of horizontal building block. They always talk about one of the guarantees they make, which they may or may not have, failed to deliver on at some point in maybe the recent past, but we're not here to argue about that, is that one AZ shouldn't affect the other. And they're thinking the same thing I'm talking about. They want to be able to say, look, if you're in 2 AZs, we might turn one off sometime, but you should be in 2, and then it's OK. And so you sort of align with the edges of the trifle, of the bottom of the trifle that you're on, and it makes things a little bit easier. Once again, the same hidden interaction we were talking about earlier. If you're in if a bunch of people are in a single AZ and that goes down, they're all going to immediately try to go to the other AZ, which you might be in, and not much you can do about that. So the recommendation is to treat every data center as an independent microcosm of your overall architecture. And so what does that mean, right? So we're going to go now into the birds and the bees. We're going to have some diagrams on the screen. So what the hell is this, right? You got a bunch of triangles, squares, arrows, stuff. Clearly, it's a merry-go-round. But not really. This guy's my favorite because he's so unhappy, but he's on a merry-go-round. What are you mad about? But let's actually label some things, right? So so this is sort of we started the center. So the center is the load balancer, and this, once again, isn't cloud unique. Things at Yahoo look a lot like this. You have your load balancer, you have your actual services that are performing the work, and you might have a queue, and the queue might sit between your services and your data store. Nothing crazy. Note the lack of specifics. That's on purpose, right? I'm not telling you what the load balancer is or what the queue is, because even this data store that's replicating all over the place, this could be MySQL if you're really masochistic, right? Like, it's fine. People have done this. So now you add the sort of data center boundaries, and you start to see that the only thing that's talking across data center boundaries is the data store, and right, that's your replication. That's where you're ensuring you have data redundancy, and that if you lose one of these guys, you still have all your data. And this diagram is simplified. There's a lot more going on. I skipped the part where there's workers pulling things off the queue and putting them in the data store, right? That's all encompassed in that arrow. So turns out now, when you need to perform a maintenance, mint.com, you don't need to put up a cute screen that says, oh, our engineers are working on stuff. You can just leave your site up, turn off one data center at a time, do your work, put it back in, turn off the next one, right? 0 downtime upgrades. Isn't that lovely? And you know, maybe some people are sitting here thinking, "Oh, this is not very exciting at all. I've heard of this before," but people aren't doing it, right? So hopefully someone's learning something. But yeah, you just turn off the flow from your load balancer to your one data center at a time, divide and conquer, and your ops guy's super happy because all you had to do was turn it off, run the upgrade, turn it back on. And before you turn it back on, the other thing you can do is if you have consumption tests that run periodically, maybe you have these, you should, that hit your API and say, hey, can I do this, can I do this, can I do this? Checklist, right? Make sure that all your basic functionality is up. You can run those on your one data center, right? You can direct them, add just the box that's currently turned off, and say, does this data center function the way our entire system is supposed to function? The whole microcosm of your entire infrastructure. What's that? One of the data centers is degraded. Oh no, turn it off. And you're done. Go back to sleep. It's 4 in the morning, right? You're paged. Your response times are up. You look, and they're all coming from the same data center. Back to sleep. You have an incompatible upgrade, your data store, right? You're going from some version of Cassandra to another version of Cassandra, for example, that the nodes can't talk that well to each other because they're using a slightly different protocol. Turns out you can handle that too. Turn off that data center, turn off the replication, upgrade one, turn it on and turn the others back off, upgrade those, turn everything back on, 0 downtime upgrade of your data center. The SQL guys in the crowd, you can do alters like this too. And this is actually a slightly simplified version of what Flickr does because they have MySQL. They don't have a ring-like data store. You have master-master replication. You turn off one half. You're on the alter. Turn on the other half. Turn this half off. Run the alter again. Turn them both on. You're done. I mean, you have to be careful with the kind of alters you run. They have to be sort of backwards compatible, but that's why you don't see like, oh, we're moving our photos around in a wheelbarrow on Flickr. Like you don't see those little cute pictures while the website is down for several hours for no particularly good reason. You don't want like those hours that Mint shuts itself down at night. That's you know, I don't go to Mint at night anymore, and those are ridiculous credit card offers that I'm not seeing that they could be making money off of. Right, sometimes you'll have something crazy happen. Your Cassandra node just starts logging crazy things. No one knows what's happening. And it happens like this, and the other Cassandra nodes don't realize it. They keep trying to talk to it. You know, it's a complex system. No one's quite figured out what's going on. It's OK, because the writes are all just going in the queue. Everything's fine. No writes are lost. The users that might be hitting that node with their data don't even know, because all they're getting is 202 accepted. We got it. It's in the queue. The queue might fill up, but we'll get to that. You can go a long time. And by the time this happens, you're probably awake now, and you saw this, and you just went, data center's off. Figure it out later. And then, yeah, if you have a spike in write traffic, right, it just goes everywhere. It goes in the queues. This is where the queues become important. Normally, the queues are sort of, you know, a lot of times you get the temptation, well, the queues are always empty. Just take them out. It'll probably speed things up a little bit. Disagree, right? This is the sort of thing where these two scenarios is where the queues can really help you, and they make other things a lot easier that aren't really operational that I won't go into. But like data migrations become a lot easier if you have a queue to go through. So you know, queues are nice. So this lever that I keep pulling over here that just won't materialize, what this is all about is they're really simple operational steps for stressful tasks and situations, right? Like an upgrade to your data store is super stressful. Your ops guy is already sweating. His ulcer is acting up. You're breathing all heavy in his ear. It's already tense, right? Or you're experiencing an outage. It's troublesome times. If you can just turn it off and then sit back and then figure out what's happening, you'll probably figure it out faster too, because you're going to be relaxed. You're not. Everything's okay. Right. So in terms of time, you separate when you found the problem from when you have to figure it out. Because if everything's coupled and this is broken, you have to figure it out now, because there's that giant graph of red with the arrows, the errors on your TV, which has your graphs on it, right? Everyone's looking at it. The errors are still there, right? But if you can separate that and the errors go away and you can just figure it out in your own sweet time, it makes everything a lot easier. People aren't assholes. Is she in here? Well, anyway, it makes it easier not to be an asshole when things go wrong, because you're not as stressed out. You can go back to sleep, right? if you're, we'll get to the specifics, but if your problem really comes down to having to turn off an availability zone to stop an outage, that's like 5 minutes probably. You wait for it to go away. You wait for the errors to go away. You go back to sleep, right? Everything's fine. You wake up the next day feeling great. Now let's. How are we on time, by the way? Oh. We got like 20 till. All right. So we're gonna make lunch. Perfect. So specifics, right? That's what we're all here for. So this is the right path, the real right path of the SimpleGeo architecture. It's a little bit. The diagram's a little bit more involved than what I was showing you earlier, but not by that much. And the reason there's two sides is just to show you that they're completely identical into data centers. So it starts at ELB, which is just a load balancer, like we talked about earlier. That was the triangle in our little picture. It goes through gate, which is a thing we wrote, but it's a really simple thing that I'll explain in a second. And it goes through, there's a number of services, but they're all roughly identical as far as their appearance and their interface. And then the writes go through a queue. A worker pool pulls it off. A worker pool pulls jobs off the queue and writes them to the data store and the index. So the index is that crazy thing I said we weren't going to talk about, and we won't because for operational purposes, it's identical to Cassandra. And we've tried really, really hard to keep it that way. So everything that I talk about doing to Cassandra, we can do to that thing too, and basically treat it exactly the same. So I don't think ELB is just a load balancer, right? There's not much to it. It's not everyone's favorite thing. There's some problems with it. It's sort of what we've got. Everyone's sort of always evaluating, right? We have thought about maybe getting off of it, but that's what's there now, and any load balancer will do, right? And then gate is the thing I just talked about that we wrote, and we refer to it jokingly as the layer 8 proxy. And the reason we say that is because it's a very, very, very lightweight thing. Basically, it's a very thin Node.js layer, and all the things it does are things that are common across services, right? It takes care of authentication, it takes care of rate limiting, and it routes the request to the appropriate service. Now you might say, well, wait, aren't you just talking about not sharing your subsystems? This thing talks to everything, and you're right. And if if gate is ever broken, everything's broken. But turn it off, right? So that's why we upgrade one AZ at a time. When we have a gate upgrade, we install it in one AZ, run the consumption tests, then turn it on. If they fail, we don't turn it on. We figure out what's wrong. I'm going to start sounding like a broken record here. So yeah, recall decoupling your functionality. Everything sits under gate, but everything's separate underneath, right? So our services are sort of a pick your own adventure thing. More recent stuff has been written in Node.js. Some people just don't like it, and that's okay. I have my up days and down days on Node. It's okay. Some things are just easier in Python, right? We do a lot of geo stuff. Manipulating polygons is brain dead in Python because someone already did all the work. Have to do all the work in Node, right? So sometimes you kind of balance it out. But that's the beauty of it, is that it could be Scala, it could be Clojure, right? It could be anything you want, as long as it speaks HTTP, because Gate can talk to it. And these services, right, are the highly specialized decoupled things we talked about earlier. So then we use RabbitMQ, and I hinted at this earlier. Rabbit is definitely, an AMQP in general, is probably has more features than we'll ever need. And when I initially got there, I'd never dealt with it before, and it was a super frustrating couple of weeks. But it works, and it works super well. And a few months ago, we went from something like 1.2 to 2.4, and it blew our minds how much better it was, right? So it's a project that's very steady. There's constant improvement. There's the new persistor that they introduced in 1.3 provides really, really nice, when you run out of memory because your data store is so hosed, it just starts writing things to disk, and it degrades a little bit, but not that much, right? You can still accept the writes. And there's a talk actually coming up right after lunch where someone's going to talk about RabbitMQ in detail. And now we're getting to the abstract I reread it this morning, and I was like, whoa. It talks about building an infrastructure that has the cloud baked in. So a distributed hash table is, when you think about it, the perfect data store choice for the kind of thing we're talking about. And the reason is is the partition tolerance, right? The homogeneous model is really nice and also important for the cloud because we evaluated a bunch of data stores and we actually looked at HBase and it would have done just fine, but if we were going to pick one, we picked the one that didn't have the single point of failure because we knew it was going to fail. And we do use HBase for some non-production processing, and the name node has failed. Like that's just something that happens. And people are working on that problem, but 2 years ago, that was something you had to live with, right? So a DHT that's completely homogeneous is ideal because you can randomly turn off nodes and everything's okay because there's no leader, there's no single point of failure, right? So the partition tolerance is the important thing because partition tolerance isn't just for outages, right? People talk about partition tolerance in terms of, well, what if your network dies, right? Like what if you can't connect to your other node? This is the context that it's always talked about. But recall our little divide and conquer series of slides where we turned off one AZ at a time and did some stuff to it and turned it back on. This is also a partition when you do that, right? And this is what I talk about when I talk about Cassandra and our architecture sort of growing out of thinking about how to build stuff on the cloud because you can turn any part of it off, or Amazon can turn it off for us if they decide to do so. And it's okay. We move on. And we use Cassandra, like I said, but the real important part is a homogeneous DHT. It could be React. It could be Voldemort, right? Anything that has those characteristics where you can take some nodes away and everyone just figures out what to do and passes the data around later in the background when you come back online. So I think that's actually it. Maybe I ended a little, what is it? Actually, no, it's not bad. Yeah, so I ended a little early, so if anyone has any questions, go ahead and ask them. If you don't, we can go to lunch. Yes? Yeah. Why wouldn't we spread across vendors? Well, so recall, there's a hidden, I admitted to that, right? The same problem exists there too. You're just not spending anywhere near the amount of time and effort maintaining it, right? And the other thing, I do have it in here. I skipped over it. So hot is basically the only way I've ever seen anything work. I can't find the slide now. But if you're going to be hot across vendors, I mean, yeah, you can do it. And it's really not that different than probably even being cross-region in Amazon. Like I said, if you want to do that, that's fine. It's just a ton more work. It's a ton. So the whole, what? You're preaching decoupling, but then you're mirroring everything to Amazon. Well, so, yes. Yes, I appreciate that, keeping me honest. But what I'm saying is that if you're hot, fine. Basically probably that's what I should have said. If you're hot across vendors, whatever. If your strategy is I'm going to spin up a bunch of nodes on Rackspace if Amazon goes down again, that's not going to work. And maybe I'm misunderstanding sort of the movement, right? But it was. The way I understood it was be prepared to spin up a copy of your site, right? And the other thing is, one of the things about the cloud, one of the reasons people build their infrastructure on the cloud, and the reason we do it is because it saves you a lot of CapEx. It's up to a certain level very cost effective. You don't have to hire all that staff. The more vendors you get into, the more whoever's responsible for that is managing, right? They're not, I mean, yes, there's some various tools for making it look opaque and the same, but here are more probably baffling interactions that you're setting yourself up for because those APIs that are supposed to be totally generic across the different infrastructures are probably not all that generic. You're opening yourself up to, oh shit, what happened, right? And now this person has to manage all those differences and all those subtleties, and maybe not all the cloud providers offer all the services you need. Now you have to figure out how to bolt stuff on at a different cloud provider. And now, before too long, it starts to look like you're just managing a data center, right? Like you might as well just, right? Why bother? So it might work, it might not, right? Like, I don't know. We. On the other hand, when yes. It's a yes. it's a cost thing, essentially, right? If you have the staff and the money and you want to be hot across vendors, sure. Anybody else? Well, that's what I'm saying, right? Okay, so where does your load balancer go? Which are you agreeing? Who are you agreeing with? Sorry. Okay, yeah. Right, because right, you have to pick like where does your actual balancer go and where does this happen, right? Like at what level, right? Is it DNS? Right? Then you wait for propagation. Who's hosting the DNS, right? Do you go somewhere? There's a lot more questions basically that need to be answered, and the list of questions gets longer and longer, and that's complexity, right? You have to balance that out. Anybody else? Okay, let's eat.